Hello everyone, I am from Institution of Aeronautical Engineering College. My name is Om Prakash. I am from CSIT. My topic is about characteristic values of arbitrary matrix. The introduction of characteristic values of arbitrary matrix. The determination of characteristic values of matrix is of paramount importance in many branches of applied science, and consequently much attention is being given to improvement of existing prevalent method as well as to development of new ones. The method described below for the determination of the characteristic value of arbitrary matrix possessing complex elements, aside from beginning news in believed to be promise, it is based on the theorem of I-Suhur, which asserts that any matrix of complex element can be reduced to triangular form by mean of sequence of unitary transformation which generate the characteristic value of matrix along the diagonal of the triangularized form. See for example McDuffie. In applying this theorem as described in detail below, the triangular part of matrix initially possessing the lower norm is chosen from annihilation. Then an arbitrary element in a triangle, example an element of above average absolute value, is selected as the pivot of a certain unitary transformation, which is determined in such a manner as to reduce the total norm of the triangle. The construction of the unitary transform having this norm reducing poverty is founded on the real roots of associated cubic polynomial with properly determined coefficients. The unitary transformation. Illustrating the procedure, the unitary transformation, let us consider n-dimensional matrix of complex elements. The sign of R does not affect the new corner element AX CT DI. However, the sign of the other elements of S are changed if the sign of R is changed. To fix matter, it is advisable to assign to R the same sign as is possessed by R. It is seen that R greater than 1 for R7 into 0, while R0 also 2 equals to 0 and R equals to 1. In the latter case, the transformation level the diagonal elements unchanged, rendering 0 values are of number interest Hermitian and skew Hermitian matrix. Let us pause to consider the effect of transmission T upon Hermitian and skew Hermitian matrix A. The matrix A is Hermitian. Here AKI equals to AIK for all I and K. Thus the diagonal elements are real and C equals to B. Equation 8 becomes AX equals to RS. A plus R2D plus ZB plus ZB. So that L is real if R is real, which will be assumed in the following equation 11, or that fact that plus dx equals to A plus D. Show the diagonal element D also to be real. Equation 9 and 10 reveal that Cx equals to 5a, and the other transformations 12 through 15 indicate that A dash Ki equals to A minus star dash. In general, thus AI and similarly AV is also Hermitian. The matrix A is the skew Hermitian. In this case, AKI equals to AIK for I, K equals to 1, 2, N, so that A equals to 0. For all I, C equals to minus B. Equation 8 leads to AX equals to R2 into ZC minus ZC, making a pure imaginary number or 0 since Oj plus Alpha equals to 0. A1 is also purely imaginary. Further, it turns out that Cx equals to Bt and A1 equals to D. Ti. In general, continuing with the second iteration, we find that A2 equals to R2 into 1 minus FT2 A plus ZB minus ZB 0 by 2. Thus A2 D2 are also pure imaginaries. Next, C2 equals to 52 and A1 V equals to A. The successive transformed matrix AV allow show the same behavior, namely that the skew Hermitian characteristic is preserved except for the elements of the diagonal which become pure imaginaries. The preservation of the Hermitian and quasi-Hermitian nature of the transformed matrix is clearly of importance in that it essentially halves the amount of combination labor involved in the entire calculations, as have been shown by the author elsewhere. Hermitian and skew Hermitian matrix can be diagonalized by unitary transformations of the type by the annihilation of the pivot. Construction of the norm-reducing cubic. T is desired to construct the variable T is in the transformation matrix T in such a manner that the sum of a square of the absolute value of all the superdiagonal elements in the transformed matrix A is decreased. Now this sum for the affected elements of the original matrix A is M equals to E AKI2 plus AKI2 plus E I by 2 plus ID plus E into I2 plus by AKI by 2 plus B 2 into 18 equals to E plus E plus E plus I and I2 1 2 3 and the summation are to be extended over 7 for E greater or less than I equals to 1 2 3 with the intervals by greater than as defined in second 2 for the transformed matrix AI. The corresponding sum is where the superscript 1 indicates that the A81 are to be replaced by the corresponding CTI. Now the transformation formula with the fact that, and this is the formula of the transformation, where is generally A equals to A into exp I axj. It is sufficient to restrict the value of 6 to interval 0 if namely R is real root of fr6 0 associated with the value of 6t. Then if we put 0i equals to 6 minus t, ri equals to r because of cm minus c2. It follows that f r1 6 equals 0. However, zi equals to ra. Stress id1 equals to r expression minus z, and if sjn r equals to sgn r, also h equals to minus r exp. The value of z as determined by the system 26 will be produced the greatest possible reducing penetration in the superdiagonal norm. Any other number z obtained by solving f into r6 equals to 0 alone for arbitrary 6t 0, 7r will bring about a smaller decrease in the norm. However, such alternate value of z may still be interset. Computational procedure. The foreign discussion indicates how the procedure may be applied in practice. A method of selecting the pivot B must be decided upon. Once the triangle of lower norm has been determined, one may take as pivot the element of largest absolute value. Any above average elements proceed cyclic to the next element in that triangle or take B in some other fashion pivot lying in the super diagonal J-I plus simplify the computation somewhat in that the case the sum in equation and to vanish with more experience better choice of pivots may become available next the selection of angle of rotation must be made for intersection into the coefficient of cubic and ultimately for the transformation itself. Here again more experience will be provided better clues. Count of arithmetical operations reveals that approximately 8n plus 8 into j dash star plus 8 multiplication of complex numbers are involved per iteration aside from the solution of cubic for an average value of n plus 1 by 3 for j dash I. This amount to be about 32 by 3 n plus 1 multiplication per iteration for each eligible element to act once as a pivot, which is the least one might accept. Dash n dash 1 by 2 iteration would be required. This would result in n dash 1 transformation of each diagonal element at a cost of about 6 by 3 n3 multiplications. This estimate seems reasonable in view of counts of 4 by 3 n3 multiplication for the reduction of real symmetric matrix. Example: in carrying out the reduction of A to triangular form, the element of largest absolute value was taken in general as the pivot, and the angle of rotation 6 was determined according to the equation. Since n dash equals to 8, n equals to 9, we have n equals to n dash. The matrix A as it appears in equation has already its upper half in the proper place. The real part of the characteristic values are thus already determined to better than 5%, while the imaginary parts are off by less than 6%. Conclusion: a new method has been presented for the determination of the characteristic value of arbitrary matrix having complex elements. The example shown above as well as additional complication evidence justify the belief that the approach is a promising one. Thank you everyone for giving this opportunity presented by T. Om Prakash from CSIT.